Welcome to lesson 2 of redox, which is how to write out reduction and oxidation half reactions. So what is a half reaction, you might be asking? Well, it is a balanced chemical equation that represents either the loss or gain of electrons by a substance. So essentially it is showing either the reduction, the gaining of electrons, right? Or the oxidation, the losing of electrons. Showing one or the other, which means it is half the reaction, because for a redox reaction, you have to have both reduction and oxidation taking place. We're only showing half of it with a half reaction. So if I take a look at this reaction, for example, which actually was the last example we did on the previous lesson, where I have zinc and hydrochloric acid making zinc chloride aqueous and hydrogen gas. So if I take a look at what I've got here happening, I have zinc starting out with a charge of 0. Hydrogen, as we talked about last time, would have a charge of +1 if we treat it as ionic. Chloride, -1, and then zinc I have +2, chloride -1, and finally I have hydrogen as an element with 0. So if I were looking at the half reaction, the oxidation for this, zinc went from 0 to +2. Let's try drawing some arrows. 0 to +2, so it got more positive. It went through oxidation, right? The poo, positive oxidation. Well, if I went from +1 to 0, just writing all over what I had here as text, that's my reduction. Because it became more negative going from +1 to 0. So as I've been talking about that nerd. So oxidation half reaction, I'm going to show the oxidation of the zinc because that's what actually got oxidized. So what I would do is I would start out by having Zn solid. And I like to actually just go ahead and go to the chemical product of this, which because it's aqueous, I can write just Zn2 positive aqueous. So a quick word on that. Whenever I have ionic compounds that are aqueous, I can just treat them as separate ions. They dissociate in solution. So when I have zinc chloride, I don't actually have zinc and chloride together. They are separate in the solution. They have dissociated and they are moving around. All right, so I've written out my zinc. I've written out my Zn2 positive, so I have my reactant, my product. You might notice that right now, things don't work out for charge. I have 0 for a charge on the left, and I have 2 positive on the right. 0 here, 2 positive here. So I need to make charge equal, and I do that by adding electrons to one of the sides. You are always adding electrons to the more positive side. I'm going to write that down here. Add electrons to the more positive side. And that's how we make it equal out, because electrons are negative. So in order to make charge equal on both sides, we have to add it to the side that is more positive, so the negatives will essentially cancel them out. To the more positive side is what I meant to say. Okay, so I have zinc here, I have 2 positive over here, so I need to add 2 electrons to the right in order for that to work. This is making it obey the conservation of mass and charge, right? I have 1 zinc atom going in, 1 zinc atom coming out, and now I have the charge equal as well, so I didn't lose any electrons. I'm showing, well, I did lose electrons, but you know what I mean. They didn't just disappear, they're being lost. All right, for the reduction half reaction, I have H positive aqueous that is going in, and then I have H2 gas that is coming out, right? So I have my H positive right here that I began with, and then that turned into H2 gas. That's what went through reduction. First thing I need to do is to make sure that my atoms actually equal out, and at this point they do not. I have 2 H's right here and I have 1 H over here. So I need a 2 in front of this, right? 2 atoms going in so that I have 2 atoms coming out. So my charge right now also is not equal. My atoms are equal, but my charge is not. I have a 2 positive charge on the left and I have a 0 charge on the right. So what I need to do to make this equal is add electrons to the more positive side, which is the left side. So I'll add 2 electrons in order to get rid of the 2 positive charge on the left, and now both sides have a charge of 0. It doesn't have to be 0, it just has to be equal on both sides, but I've accomplished that at 0 in this example. Oxidation, electrons will always be a product. Well, for reduction, electrons will always be a reactant. In reduction, I'm gaining electrons, right? So it's a reactant. In oxidation, I'm losing electrons, so it's a product. This might remind you of exothermic and endothermic. When I had exothermic, I lost energy from the chemicals, right? I let out heat, so energy was a product. And in endothermic, I gained energy, right? So gained energy, so it would be a reactant in that case. In the same way, I'm gaining electrons, so it's a reactant in this case. Okay, so kind of some connections there. So some important things to remember whenever we're doing redox. Number one, charge and atoms must balance on both sides of a half reaction. They have to, and that's kind of the process we went through in that last example. And then, like I just actually mentioned, in oxidation, electrons are in products, and in reduction, electrons are in reactants. Now I can actually combine my two half reactions after the fact to make what's called a net reaction. When I do that, I have to make sure electrons in both half reactions are equal. So I can multiply the full half reactions, everything in them, in order to make electrons equal. And the idea of that is you need to make them cancel out so that the electrons do not show in the net reaction. In other words, the electrons lost have to equal the electrons gained in both in order for us to make a proper net. This might remind you of Hess's law. It is kind of the exact same thing of I'm making sure that electrons cancel out on both sides before I combine to make my net. So just going back here, again, you may have to multiply everything in one of the half reactions to make it equal to the other. Okay, so let's take a look at an example. Here I have a reduction half reaction, so I'm reducing chlorine by adding 2 electrons to make 2 chlorides. So notice it's reduction. I have electrons as a reactant, and notice that the charge on both sides is equal, right? I got 2 negative on the left, 2 negative on the right. In oxidation, I have aluminum turning to Al3 positive aqueous and 3 electrons. Again, take a look. The charge is equal, 0 on the left, 0 on the right. So these are valid half reactions. So if I take a look at electrons, in order for it to cancel out, I have 2 in the reduction. I have 3 in the oxidation. That's going to meet up at 6. So that means I need to multiply this one by 3, and I need to multiply this by 2. And that will make both equal at 6 electrons. So now if I write my net, I just have to make sure that I've obeyed multiplying it through the full half reaction. So my 2 reactants now are 3Cl2 aqueous, and I have 2 Al solids. And then that gives me 6 chlorides and 2 Al3 positives. I'm not writing out the electrons because they have now canceled out. They're gone because I made sure that they were equal on both sides. I would have had 6 electrons over here and 6 electrons over here, but again, they go away because I have made sure they're equal in both reactants and products, and they're gone. There is a fantastic way to check every single redox reaction, whether it's a net or a half or whatever. And in fact, if you were taking the diploma, it is like a cheat on diploma exams because you can actually eliminate options based on this. So clickbait here, one simple trick to make, I don't even know how to put it, simple trick to get rid of options on your diploma, to cheat on your diploma exam that you're not going to have. So what you can do is you can actually take a look at the charge on both sides and just make sure it's equal. You can do this for a half, a net, whatever. Often on the diploma exam, they would have options where it does not actually equal out. So if I had 3Cl2 aqueous and 2 aluminums, the total charge on this side is just simply 0. And then on the right-hand side, I have 6 negative, 6 positive. So that also adds up to just actually be 0. So I check my reactions with that for redox to make sure that it's valid, and it does work out. It's the same on both sides. Again, it doesn't have to be 0. It just has to be equal between reactants and products. Okay, here's another example, quite similar. I still got some chloride stuff going on with that zinc and chloride one. So take a look, maybe try this out first and then come back to the video and see if you're right. So pause it here, give it a try, come back. Okay, here's a solution. So oxidation half reaction, I'm going from 0 with chlorine right? I've got +1 for hydrogen, -1 for bromide. Over here I have +1, -1, and 0. So again, elements are sitting at 0, and then I'm treating these as ionic compounds and writing down what the charge would be for the cation, the anion, so +1, -1. So as you can see, chlorine goes from a charge of 0 to a charge of -1. It's getting more negative, so this is reduction. So NER, right? Negative reduction. Well, if I have bromide going from -1 to 0, this became more positive and went towards the positive end. So this is POO, positive oxidation. So if I want to do my oxidation half reaction, that's happening to bromide. This is aqueous, so I can treat it as split apart ions here. So what I have is I have Br minus aqueous, and this is turning into Br2 liquid. I feel like I just kind of left out a little bit of nuance here. This is a strong acid, right? So because it's a strong acid, I can treat it as the positive hydrogen is separate from the negative bromide. So now that I have Br minus and Br2 liquid, I take a look and realize that my atoms don't work out. I need to have 2 bromides in order to have Br2 coming out of it. So I have 2 bromines going in, 2 bromines coming out. And now if I look at the charge on the left-hand side, I have 2 negative and I have 0 on this. So I need to add electrons to the right-hand side to make it equal, and that will be 2 electrons. So now I've met up with both sides having a 2 negative charge for the oxidation. For the reduction, I have Cl2 gas, and that is turning into Cl minus aqueous. You'll notice I actually just kept this coefficient out of it. I like to work that out afterwards. I just like to write out everything without coefficients and then fix that after the fact as we finish up the half reaction. So I have 2 chlorines going in, I have 1 coming out, so I need a 2 there to make the atoms equal, and then for the rest I need to add 2 electrons to the left in order for me to get 2 negative on both reactants and products. So again, making it equal. All right, so now if I was combining to a net, I would take a look at my oxidation, excuse me, and I have 2 electrons in my oxidation, and I have 2 electrons in my reduction. That's equal. I'm all good to go. So I'm really multiplying both of these by 1 or not at all, right? Because the electrons equal out. And again, the whole purpose of this is to make sure the electrons equal when I combine to make a net so that electrons cancel out in both reactions. So now that I've seen that, I can actually just rewrite this. So 2Br minus aqueous plus Cl2 gas makes Br2 liquid and 2Cl minus aqueous. Not writing the electrons, they cancel out. Quick double check here. When I have the left-hand side, I have a charge of 2 negative from the 2Br minus, and on the right, I have 2 negative from the 2Cl minus as an overall charge. So we're good. This is a good reaction for redox. And then also the atoms, of course, are balanced and work out as well. So we're all set. All right, another example here. Let me just quickly flip ahead to see what we have left. We got, 2 more examples. So again, maybe pause it here, give it a try, and then come back. So pause now. And here's the solution. So I have 0 for aluminum, +1 for hydrogen. Nitrate, we're just going to kind of treat as one ion right now as -1. Again, we'll get fancier with these kind of polyatomic ions later on, but I think it's obvious what's happening here. Aluminum is becoming more positive, while hydrogen is becoming more negative, going from +1 to 0. Okay, so aluminum is again becoming more positive, so this is my oxidation, while hydrogen is my reduction. So my oxidation half reaction, I'm going to leave the coefficients out of it. I have Al solid, and that is turning to Al3 positive aqueous. Now, I'm going to put the electrons on the more positive side, so that would be the 3 positive side. So I'm going to add 3 electrons in order to make that equal. Again, oxidation has electrons as a product, right? I'm losing electrons, it's going away, so it's over there. For my reduction, again, I'm going to leave coefficients out of this, so I have H positive aqueous, and that is making H2 gas. So now I need to make sure that my atoms equal out, so I'll put a 2 in front of H positive, and then I'm going to put electrons on the more positive side, which is on the left. I need 2 electrons to make this equal. So 2H positive plus 2 electrons gives me H2 gas. So now if I take a look at both reactions, I have a 3 positive here. Sorry, 3 electrons in this half reaction, the oxidation. And then I have a 2 negative in my reduction. These are going to meet up at 6. So if I take 3 electrons times 2, I get 6 electrons. And if I have 2 electrons times 3, then I get 6 electrons. So it meets up at 6. So what that will end up giving me is for reactants 2Al solid plus 6H positive aqueous, right? Because I multiplied this by 3. Got to be really careful that you multiply everything through. Gives me 2Al3 positive aqueous and 3H2 gas. So I have 2 aluminums, that's all good, 2 and 2, and I have 6 hydrogen atoms, so that looks good. Let's look at charge. I have 6 positive on the left, and I have 2 times 3 is 6 positive on the right, so it works. It's all good. It's a good half reaction. So what happened to nitrate? Nitrate is a spectator. It doesn't actually do anything in this reaction. It just is watching. So we don't write anything for nitrate because it is a spectator ion. It is not a part of the oxidation or reduction. Okay, one last example here and then a bit of a summary table. Now, a quick note for this. I wrote this out as aqueous for these iron oxides. In all reality, I realize it's not soluble or very soluble for these compounds, but I want to keep things as ions dissociated. So we wrote aqueous for our purposes, but I realized these actually would be normally solid compounds when they're placed in water. But let's just roll with it in order for us to be able to split it apart into ions. All right, give it a try and pause and then come back, and here's the solution. So here we go. In iron 2 oxide, this is 2 positive and this is 2 negative. In oxygen, it's 0 because, again, an element. And then here I have 3 positive and 2 minus for the oxide. So if I take a look at what is going through oxidation, I'm looking at what became more positive. And the thing that became more positive is actually the iron 2. So this went through oxidation. What became more negative? Well, this oxygen did. And now not all oxygen did, but the O2 oxygens did. And this went through reduction, right? So more positive, oxidation, poo, and then more negative, going from 0 to 2 negative, ner, for reduction. So my oxidation half reaction then is I have Fe2 positive aqueous turns into Fe3 positive aqueous. And I have an electron on the right-hand side so that I match up the 2 positive on the left with 2 positive on the right. So again, I add electrons to the more positive side. It's losing the electron. For the reduction half reaction, I have O2 gas because that is what is actually getting reduced. And that is becoming essentially O2 minus aqueous. So notice I'm writing out just one of the ions here. So in order for me to make this work, I need 2 of the O2 minuses. That means I have 4 electrons on the left, adding those electrons to the more positive side in order to make charge equal on both sides. So now I've got 4 negative and 4 negative. What I should have actually been doing the previous examples is to actually label both the Ra and the OA just to kind of reinforce those concepts. So in this scenario, this iron 2 is actually the Ra because it went through oxidation, while this oxygen is the OA, right, the agent for oxidation, because it went through reduction. So the agent is the chemical that is the opposite of the process I went through. Okay, so what got reduced, that is the OA, and what got oxidized, that is the Ra. So now if I try to do my net ionic, you'll notice that I have 4 electrons in my reduction. I have 1 electron in my oxidation. So this, I'm going to need 4 of them in order to make that work out, right? So 1 and 4 meet up at 4. So I end up with 4 Fe2 positive aqueous plus O2 gas. Didn't have to multiply that one at all, so we're all good. Makes 4 Fe3 positive aqueous and 2 O2 minus aqueous. If I take a look at the overall charge, on the left-hand side, I have a total charge of 8 positive, right? 4 times 2 positive. And on the left, I actually have 12 positive here plus 4 negative. So that equals 8 positive in the end. So my reactants and products, they equal out. They work. Okay, so a little bit of a summary table here. What I've got is some chemical species, different types. So we'll kind of talk about what an example would be for each type. Whoops, moved forward. So metal ion would be something like Zn2 positive, right? Metal element would be something like zinc. Non-metal element would be something like, let's say, chlorine. And then non-metal ion would be something like chloride, for example. So if I were to talk about what a metal ion goes through, so I have a 2 positive ion, for example, it's going to go through reduction. It is positive, it's going to become more negative. So metal ions go through reduction, and as a result, it would gain electrons and it would become more negative, and it would become a metal ion or metal element. So by actually gaining electrons, it becomes a metal element instead of an ion. Typically, the only exception would be multivalent metals, where maybe it goes from like titanium 4 to titanium 2, whereas you saw in the last example, where it actually changed from iron 2 to iron 3, right? That was a reduction, but it didn't go all the way. So multivalent metals can kind of be an exception. That was a bad example because that was actually a reduction instead of oxidation. But oh, and I'm screwing that up. No, that was, sorry, let's get this straight. This was an oxidation, not a reduction. In my table, I'm talking about reduction. All right, metal element, zinc. That would go through oxidation. It would lose electrons to become a metal ion. So we'll put that right there. If I have a non-metal element, that would go through reduction in order to become a non-metal ion. And if I had a non-metal ion, that would go through oxidation, right? It would lose electrons in order to become a non-metal element. So I don't know if that helps, but that's kind of the typical species that we have in terms of chemicals, and then the process they go through, and then what they become. Okay, so exception, I already talked a little bit about this, but I kind of messed up how I talked about it. Metal ions that are multivalent can be further oxidized, or they can be reduced to an ion with a lower charge. So then it wouldn't maybe form the element, right, as talked about here, but it might do something else. So let's take a look at some examples going forward to the next slide and kind of show you how that would look before we finish up here. We're already at 22 minutes for this recording. All right, so oxidation of multivalent cation from ion to ion. If I take a look at this, this titanium is titanium 3 and it's going to titanium 4. So it's going from a 3 positive to a 4 positive charge. So if I were to write the oxidation half reaction, I would have Ti 3 positive aqueous, right, goes and reacts to form Ti 4 positive aqueous. I would add an electron to the more positive side, which is this one. So it oxidized from an ion to a more positive ion. So this is essentially still an oxidation, but it didn't end up going from an element to an ion. It went from an ion to a more positive ion. Okay, now let's try this next one. I just want to actually move up this slightly so that you can see it on the screen. All right, here we go. So let's take a look at this one where I have manganese with a 4 positive charge, right? Because oxide is 2 negative here. And then I end up with a 2 positive charge, oxide 2 negative here. So here I'm again going from one ion to another. So I would have Mn4 positive aqueous turning into Mn2 positive aqueous. And I would add 2 electrons to the left in order to make that work. My 4 is horrible here. Let's try that again so it's a little bit neater. All right, so there we have Mn4 positive plus 2 electrons making Mn2 positive. So going from a higher charge to a lower charge, and that still also is reduction. Okay, that's it. That is half reactions. Try out some work on this, see how it goes. We are going to later on do a lesson on more complex half reactions. So we have to do a little bit more work adding hydrogen ions and waters and stuff in order to make atoms and charges balance. But that will be a later lesson. All right, have a good rest of your day.